Hello guys, welcome to my presentation. My name is Jiang. This is for CS520. Today we're going to talk about prime factorization algorithm. The objective for this presentation is we are given a number n, then we're going to write a function to print all the prime factors of this number. And this includes the general algorithm, and we're going to use a Java code to prove how this algorithm works. And we're going to look at the runtime for this algorithm. By definition, factorization consists of writing a number or another mathematical object as the product of several factors. Let's do a quick example here. If you are given a number 40, 40 can be broke down into 4 times 10. So we say 4 and 10 are the factors for 40. However, 4 can be further break down into 2 times 2, and 10 can be break down into 2 times 5. And at this point, you cannot break down anymore because 2 and 5, they are prime numbers. So we say the prime factors for 40 is 2, 2, 2, and 5. So remember that prime numbers, it's the number can only divisible by itself or 1. So for example, 2, 3, 5, 7, 11. So we skip 9 here because 9 is not a prime number because it's divisible by 3 times 3. And prime number can be a large number as well, like 137 is a prime number, and it can be a huge number. So in the next couple slides, we are going to learn how to find these prime factors of a number. In order to find the prime factors of a given number, let's use this algorithm. So in the very first step, it's always to determine if the number is an even number. For example, let's say n equals to 276. So that's an even number. So if that's even, that means it's divisible by 2. So after you divide this number by 2 and you write down 2, and the new number, if that's still an even number, you can just repeat this step, keep dividing by 2. So we have another division of 2, so we get 69. So that's no longer an even number. So that becomes an odd number. Then we go to the next step. So in here, we have 2 and 2 as the factors. Step 2 is to do with the odd number. From the previous step, we have n equals to 69, which is the odd number. So we will start a loop from I equals to 3 to square root of n, which is 69. Square root of 69 is 8.3. So inside this loop, we are going to use 69 divided by 3. So you get 23, which is a whole number. So that means we are going to print 3 in this case. Then you are going to repeat this until the number is not divisible by I. So that means you are going to try 23 divided by 3 again, which is not divisible. Then you're not going to print anything. So if you have that, then you are going to move to the next step. So here you are going to increase I by 2. So that means I becomes 5 right now. And you try to divide 23 by 5, which is not divisible. Then you keep adding. If you meet another number that's not divisible, then that means the next number is I equal to 7. 23 divided by 7 is still not good. Then you increase by 2, you get I equals to 9. But that's already greater than 8.3, which is the boundary for the loop. So that means you have to stop right here. You don't have to do this step. So that the last step is actually I equals 7. So inside the loop, you actually just print 3. And you try all the other I number, but they are all not working. Then you move to the next step. In step 3, we're going to print out the last prime factor of the original number. So from the previous step, we try to use 3, 5, and 7 to divide that to 23, but they are all not divisible. So that means 23 must be a prime number. So that means 23 is a prime factor of the original number. So as the result, 276 has prime factors of 2, 2, 3, and 23. So that concludes the algorithm. So let's do another example to practice what we just learned. To the right, we have the Java code, which will provide more details to explain the algorithm. So in step 1, let's set n equals to 315. So if that's an even number, that means it's going to divisible by 2. So in this while loop, it's step 1. So if n is divisible by 2, then you print 2 and divide that number by 2. You keep doing this until you get an odd number. So in this case, we don't print nothing because that number is not an even number. In step 2, we're going to look for the odd factors of number 315. So to the right, we have the Java code. For the for loop, inside the for loop, we're going to make I equals to 3, and I must be less than or equals to the square root of 315, which is 17.75. And in each round, the value for I is going to increase by 2. Inside the for loop, we have the while loop, so it means as long as n is divisible by I, you're going to print out the value for I, and n is going to be updated. So let's start from 315 divided by 3 equals 105. It's divisible, so that means you're going to print out 3 using this line here, and 105 becomes the new n, and 105 divided by 3, it's divisible, it's equals to 35. So we print out 3, then we're going to let n equals to 35 in this case. And then the next move, since 35 is no longer divisible by 3, so we're going to get out of the while loop and jump back to the for loop, and I is going to increase by 2. So that means the new value for I is 5, and using that value, and we using 35 divided by that, you get 7. Again, it's divisible, so we are going to print out 5 here, and 7 becomes the new value for n. And then 7 divided by 5 is not a whole number, it's not divisible, so we're going to jump back to the for loop, and I becomes 7 here, and using 7 divided by 7, you get 1, it's divisible, so we print out 7, and 1 it's now the value for n, and because 1 divided by 7, it's not a whole number, so we're going to add 2 to I. If you keep doing that, because 1 is part of the smallest number, so you no longer divisible for any number of I, as I is going to be increased by 2 every time. And I equals to 11, 13, 15, 17, until you hit 19, because 19 is already greater than the value of square root of 315. So that will end the for loop. So that's the end of the step 2. So in step 3, since n is equals to 1 and 1 is less than 2, and if you look at the coding part here, you only print the number, the prime number, if and only if n is greater than 2. So 1 is less than 2, so we're not going to print anything. We're going to just skip step 3. So the final answer for the factorization of the number 315 is 3357. So what is the runtime of this algorithm? Every composite number has at least one prime factor less than or equal to the square root of itself. So this property can be proved using the counter statement. Let's say a and b are the two factors of n, such that a times b equals to n. If both a and b are greater than the square root of n, then a times b greater than square root of n times square root of n, which is contradict the expression of a times b equals to n. And this will conclude the runtime of the upper bound, the bit O for this algorithm, it's square root of n. So let's use 2 examples to prove this. The first example, we're going to use powers of 2. Since you know 2 is the smallest prime number, that means 2 times 2 times as many times as you want. That resulting number is going to be divisible by 2 as many times as you want. So let's do an example here. 256 is divisible by 2, and you get 128. Then it's also divisible by 2, you get 64. So you are going to keep dividing by 2 until you hit 1. So that means the algorithm is going to stuck in the step 1. Every time you divide by 2, you print out 2 here until you hit 1. So after step 1, you're going to skip step 2 and 3 because 1 is already less than 2. So that means the factorization of 256, it's 2 times 2 times 2, and you times 2 8 times. So in other words, that's 2 to the 8th power. So that means you're going to use a step to finish the algorithm, which is bound by the bit O. In this case, the bit O in this case, it's square root of 256, which is 16. So 16 is greater than 8. So this is true. The second example here, we're going to do the algorithm with the prime number. The prime number I pick is 2, which is the smallest one. 2 is an even number, so we're going to use step 1 to do that. So 2 divided by 2 is 1, and we print out 2. So it only takes 1 step to finish the entire algorithm. And by definition, The upper bound or the bit O of the algorithm, it's a square root of the number you pick. In this case, it's 2. The square root of 2 is 1.414, which is greater than 1. 1 here means the number of steps you take to finish the algorithm. So that means the runtime of this algorithm is bound by the square root of the number you pick. So we just prove what we just showed in the previous slide with these 2 examples. So these are the reference I use in this presentation, and I hope you guys enjoyed the video, and thanks for watching.